Okay, so in this second video for Unit 5, what we're going to see are algebraic properties of the limits that will help us compute different limits. Okay, so if we try to apply the definitions that we saw in last video in order to compute the limits, it will be very hard in many cases. So that's why there are some properties that have been proven that we can use, and they're very useful. Okay, so let's start with the first proposition. Let f and g be two real functions such that the limit of f when x goes to a, right, is L, and the limit of x when x, the limit of g when x goes to a is L prime, right? Then we have these three properties, right? The limit of the sum of f and g, or the subtraction of f and g, is the subtraction of the limits, or the sum or the subtraction of the limits. Okay, so there's a typo here, right? So it's f minus g, the limit is L minus L prime, right? Now the limit of the product is the product of the limits, right? And finally, the limit of the quotient is the quotient of the limits if L prime is different than 0. If it's 0, then it's a different thing, okay? Now these properties hold also in the case a is plus or minus infinity, or even for one-sided limits, okay? Now, so yeah, these are kind of straightforward. They're easy to prove, actually, right? And very similar to the ones we saw in sequences, right? So the second proposition, let f be a real function such that the limit when x goes to a of f is L, right? Then the following properties hold. F is bounded in an environment of A, right? So an environment of A in the real line means this, right? So we have A, so this is a point in the real line. An environment is an interval. It could be open, it could be closed. A plus epsilon, A minus epsilon, okay? It's suppose, or A minus plus minus delta, whatever, okay? Where epsilon is supposed to be a small number, right, around A. But the idea is that around, if f is bounded in an environment of A, that means that f will be, we can find an epsilon, okay? It doesn't matter how small for which f is bounded, okay? So for instance, if you think of a function like this, x squared, as always, right? And you know that the limit when the function goes to a is this, right? Now around a, the function is bounded above and below, okay? It doesn't diverge, okay? You can always find it doesn't matter how small you need to find it, but you can always find an interval around a in which the function is bounded, right? So this is the environment around, that's the idea, okay? Now if the limit is different from 0, f has the same sign as L in an environment of A, okay? This is the same idea here, right? If L is different from 0, the function will not be able to cross over to the negative side or positive side if the limit is negative in an environment, right? That's the idea of the of this limit, right? The function around the limit behaves similar to this limit, okay? That's why the limit is so important, and we will see, you know, in the next units how these ideas make us understand functions very much better, right? And finally, if g is another function such that the limit when x goes to b of g is a, but g of x is different than a in an environment of b, right, then the limit of f composed with g in when x goes to b is L, right? So let me explain this better, right? So we have g, right, that takes the point b, takes it, function g takes b to a, right? And then a is mapped, or around a is mapped by f to L, right? That this is if b and a is in the domains of g and f, but this doesn't have to be necessarily the case, right? So the idea is that when you're here, like let's say, I don't know how to plot this, but you're here close to b, right? and this is an environment of B. Now G is going to take this around an environment of A, right? In particular, the limit when it gets closer to B is going to be closer to A, right? And now, so around B, it's going to get closer to A, and so that's why F will take this to L. Okay, this is the intuitive understanding behind that. You can prove it rigorously, but we're not going to do it here. Okay. Now, if L is greater than 0, if this limit is greater than 0, then that means we can use two examples of this, right? The limit of the logarithm of f is the logarithm of L, right? So we have the limit when x goes to b of f of g of x, right? It's going to be L. Well, if in this case what we're saying is that how to say this? In this case, this f is g. Okay, maybe it's confusing. So you're composing the log with f, right? So the limit is the logarithm of L, right, which is the limit of f, right? So I hope this is clear, right? So the limit of g when x goes to b is a, so then the limit of f composed with g is the limit of f when x goes to a, right? And so this is the same thing, right? This is the limit of the logarithm when f goes to b, right? But when x goes to b, f of b in this case is going to be L, right? So this is the logarithm of L. And the same thing with the power, right? The limit of f of x to the alpha for any alpha is L to the alpha, right? Okay, so the limit of the logarithm is the logarithm of the limit, and the limit of the power of something is the limit to the power of something. Okay, and so we can use this last property to prove that the limit of when x goes to a of x to the n is a to the n, right? Which maybe some, all of you may think, well, this is kind of obvious, right? But so what we do is we take the limit of x when x goes to a is a. You can apply the definition to this, and it's pretty straightforward, and then apply this property to prove this for every n. Okay, when here n is a real number, every real number. Okay, so it could. Now polynomials, you have a sub n, x sub n plus a sub n minus 1, x sub n minus 1 plus blah 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 plus a sub 1 x plus a sub 0. Polynomials are just linear combinations of powers of x, right? So we have this here, right? The product and the sum, we apply this here, and so the limit of a polynomial, the limit of any polynomial when x goes to a, p of x, right, is just p of a. We just substitute, right? Now this, what this means, and we will see this in the next unit, is that the polynomials are continuous functions, because continuous functions are the ones that fulfill this property. The limit when x goes to a of the function is the function at that value, okay? But not all functions have this property. Remember the Heaviside function in the previous video, right? It's also, we can also apply these properties to prove that rational function, okay, like this, will be Pn of a divided by Qp of a, right? When n and p are the degrees of those polynomials in the rational function. But this is only true if this is different than 0, okay? So if a is not a root of this polynomial. Okay, so this is kind of easy to compute the limits of polynomials and rational functions. Now we have a version of the sandwich rule for functions, which is very similar to the one we saw for sequences. So okay, so we have the limit of g when x goes to a is equal to the limit of h when x goes to a is L, and in an environment of a we have this. Okay, so f is bounded from below by g and from above by h. Then the limit of the limit of f when x goes to a is the L, right? and the rule is valid if a is plus or minus infinity and L is plus or minus infinity. Okay. First consequence of this is that the limit, when the limit of the absolute value of a function, right, is 0, this implies that the limit of the original function is also 0, because we can bound the function from above by the absolute value, and we can also bound it from below, right? So it's either the function is either smaller or greater than the absolute value, right? Sorry, minus this. It's either minus the absolute value is going to be smaller than. Okay, so if the limit of this is going to 0, right? We have that the limit of this is going to 0, as we have seen in sequences, right? Now, let us see a couple of examples of this, right? So we have the limit of, when x goes to 0, of x squared times the sine of 1 over x, right? Now we can't apply the algebraic properties that we have just seen, right? Because the sine of 1 over x doesn't have a limit when x goes to 0, right? You see the sine of 1 over x is this function that we've seen in the exercise, right? It oscillates a lot, and it gets more and more oscillating when you get to 0, right? But we know that the sine of 1 over x is always going to be bounded between minus 1 and 1, right? So if we multiply this inequalities by x squared, we have this. So our function x squared times the sine of 1 over x is bounded by minus x squared and x squared. And if we take the limit of when x goes to 0, this is going to 0, this is going to 0, so the limit of this is also going to 0. Okay, and in this case, it's the bounding by the multiplication by this number that makes this function convergent at 0, right? And so we can plot. You have in the lectures the actual plot of this function, but let me try and plot this here. So this is x, and so the x squared looks something like this, right? We've plotted this before. And minus x squared, right? Something like this. Whoop. Okay. Well, x squared times the sine of 1 over x is going to be bounded by this, so it's something like this. This is, oscillating a lot, and then it does something like this, right? Does something like this, and then the other way around. Okay. I'm very bad at plotting, but you see the idea. The oscillations are always going to touch the parabolas, right? Because when the sine of 1 over x is minus 1, then it goes like this, and then when it's going 1, it goes like this, and so on and so forth. Okay? And then let me give you another example here of where the limit where x goes to a of the square root of x is the square root of a, right? If a is greater than 0. And for this, we're gonna use again the sandwich theorem. So that when the limit, when x goes to a, and we can say that we want to prove this, right? That the difference of this is going to be 0, right? But this is also equivalent to proving that the absolute value of the difference is 0, right? If the absolute value of this difference is 0, that means that the difference is 0, and if the difference is 0, that means that the absolute value is 0, right? So it's the same thing. So we know that in order to prove this, we know that 0 is smaller than or equal than the difference, right? Because the absolute value is always positive. Now we multiply and divide by the conjugate, so we have in the denominator we have square root of x plus the square root of a, and then here we have x minus a, and in the denominator we have positive numbers, so we can, this is x minus a, the absolute value, divided by the absolute the square root of x plus the square root of a. Okay, we have this. Now this is going to be smaller than because the square root of x is going to be positive around or close to a, okay, because a is positive. So this is smaller than this, okay. When you have a denominator is greater, this is smaller. And now if we take the limit here, okay, the limit of this is going to be 0, okay. So the limit of, sorry, let me say this again. We have 0 is smaller or equal than the difference between the square root of x minus the square root of a, which is smaller than this, okay. Now we take limits here, the limit when x goes to a of this, the limit when x goes to a, and the limit when x goes to a of this is 0, okay. This is 0, this is 0, and so that means that this has to be 0, which proves the original result, okay. Now you can try and use the same argument in order to prove that the limit when x goes to a of the nth root of x is the nth root of a, using kind of the same argument and this identity that we have seen before, and it comes on you know, over and over again, because it's very useful actually, right? So try to do it on your own. And okay, so now we can also translate the or use the equivalences that we had seen for sequences. So the limit when n goes to infinity of the sine of epsilon sub n is 0, where epsilon sub n is a sequence that fulfills this, okay. It's a sequence that it has a limit 0, right? We also know that the limit when n goes to infinity of the cosine of epsilon sub n is 1, and this limits, right? The limit when n goes to infinity of the sine of epsilon sub n divided by epsilon sub n is 1, and the limit when n goes to infinity of 1 minus the cosine of epsilon sub n divided by epsilon sub n squared is 1/2. Okay, these things we know from our sequences, right? Well, we can use the definition of limits using sequences, right, to prove these limits. The limit when x goes to 0 of the sine of x is 0. The limit when x goes to 0 of the cosine of x is 1. The limit when x goes to 0 of the sine of x over x is 1. And the limit when x goes to 0 of 1 minus the cosine of x divided by x squared is 1/2. Okay? Now, with these limits and using trigonometric identities, you can have that the limit when x goes to a of the sine of x is the sine of a, and that the limit when x goes to a of the cosine of x is the cosine of a. So this is the actual proof that these two functions are continuous, which we'll see in the next unit, right? We can prove this from here, right? So let me erase this and, for instance, use the cosine, for instance. Okay, so we have the limit when x goes to a of the cosine of x, right? We can rewrite this because there's a limit when something goes to 0, okay? When the t goes to 0 of the cosine of a plus t, right? This is the same thing, right? A plus something that is going to 0, right? We can use the formula for the cosine of the double angle, right? So we have the cosine of a times the cosine of t minus the sine of a times the sine of t, right? Now this is equal to the cosine of a times the limit when when t goes to 0 of the cosine of t, but this is this limit, which is 1, and then this is minus the sine of a times the limit when t goes to 0 of the sine of t, which is 0. Okay, so the limit when x goes to a of the cosine of x is the cosine of a, right? You can do the same thing with the sine using this strategy, right? And the formula for the double angle, right? And similarly, we have our asymptotic comparisons for functions, right? So as just as we had when n goes to infinity, two functions behaved similarly. When we can have the same thing when x goes to a, and a doesn't have to be infinity, right? could be any number. And so two functions will behave similarly. We say that they're asymptotically equivalent, right? So let f and g be two real functions that either both diverge or both converge to 0 as x goes to a, right? Well, we say that f and g are equivalent when x goes to a, and denote it like this. So this is the same symbol that we used before. X is similar to equivalent to g as x goes to a if this limit is true, right? So using this, we can rewrite the equivalences that we saw in unit 3 like this. So we have the logarithm of 1 plus x is asymptotically equivalent to e to the x minus 1, right? Which is asymptotically equivalent to the sine of x, which is asymptotically equivalent to the tangent of x, which is asymptotically equivalent to x when x goes to 0. Okay, that's important. When x is very small, these functions look the same, right? And as I've told you before, the idea behind this is that if you plot this function, right, and you get closer to 0, they all look like a line, right? So the logarithm looks like this. Okay, very close to 0. This is the logarithm of 1 plus x. Very close to 0. The exponential look like this, e to the x minus 1, and this is understandable because these two are inverse function. The sine of x looks like this, okay, and around the line it looks very similar. Okay, all these functions look very similar to the line. Let me see, the tangent does something like this. Okay, around this is the tangent of x. Around 0 it does something like this. Okay, and then finally we have that 1 minus the cosine of x is asymptotically equivalent to x squared over 2, again when x goes to 0, and that means, as I told you, that 1 minus the cosine looks like a parabola when it's very close to 0. Okay, and yeah, so this asymptotic relationships that are very useful when computing limits, and in general to understand how these functions behave. We'll derive them in a more natural and systematic way when we get to unit 8 on Taylor expansors, which is actually about how functions behave close to certain points. Okay, so that's the end of this video.